Hello everyone, welcome to the Chemical Safety Technology course. I am your instructor, Suo Yanbo. In this session, we will explore the fundamentals of explosions. At approximately 6 p.m. on August 4, 2020, a massive explosion occurred in the port area of Beirut, the capital of Lebanon, resulting in at least 218 deaths, over 6,500 injuries, numerous missing persons, and 300,000 people left homeless. Lebanon's Ministry of Public Security stated that the explosion was linked to 2,700 tons of ammonium nitrate stored at the port. So, how do we define an explosion? An explosion is a phenomenon in which a substance instantaneously releases a large amount of gas and energy in the form of mechanical work. Its primary characteristics include a rapid rise in pressure, accompanied by a loud bang and a shock wave. In chemical production, an explosion can lead to casualties and result in significant loss of life and property. Depending on the source of explosive energy, explosions can be classified as physical explosions or chemical explosions. A physical explosion refers to an explosion caused by changes in physical factors, such as temperature, volume, or pressure. Before and after a physical explosion, the chemical composition of the explosive material remains unchanged. A boiler explosion is a typical example of a physical explosion. A chemical explosion refers to an explosion caused by a substance undergoing a chemical reaction within a short period of time, simultaneously producing large amounts of gas and energy. Before and after a chemical explosion, both the properties and chemical composition of the substance undergo fundamental changes. Based on the instantaneous combustion velocity, explosions can be classified into deflagration, explosion, and detonation. In deflagration, the combustion velocity of the substance is several meters per second. The explosion causes little destructive force and produces a relatively quiet sound. Examples include the rapid combustion of smokeless powder in air, and the explosion of a combustible gas mixture when it is near the upper or lower explosive limit. In an explosion, the combustion rate ranges from tens to hundreds of meters per second. It causes a sudden surge in pressure at the point of ignition, resulting in significant destructive force and a deafening sound. A detonation is characterized by the sudden generation of extremely high pressure and the production of a supersonic shock wave. The shock wave, sustained by its own energy, propagates rapidly and can exist independently far from the source of the detonation. It can also trigger the explosion of other explosive gas mixtures in the vicinity, resulting in a secondary explosion, sympathetic detonation. Based on the chemical reactions occurring during an explosion, chemical explosives can be classified into the following categories. First, simple decomposition explosives. These substances decompose into their constituent elements upon detonation, generating heat during the process. Examples include copper acetylide, silver acetylide, and nitrogen iodide. They may detonate upon friction, impact, or even slight vibration. Second, complex decomposition explosives. These include various oxygen-containing explosives, which are slightly less hazardous than simple decomposition explosives. When oxygen-containing explosives detonate, they are accompanied by a combustion reaction, with the oxygen required for combustion supplied by the decomposition of the substance itself. Examples include picric acid, TNT, and nitrocellulose. Third, flammable mixtures. These refer to explosive substances composed of combustible materials and oxidizing agents. All mixtures of flammable gases, vapors, and combustible dusts, with air or oxygen, fall into this category. The explosion limits are generally used to assess the fire hazard posed by gases and dusts. Mixtures of flammable gases, vapors, or dusts with air do not ignite or explode at any concentration. Rather, combustion and explosion can only occur within a specific concentration range. For flammable substances, including mixtures of flammable gases, vapors, or dusts with air or oxygen, the concentration range within which an explosion can occur upon contact with an ignition source, is known as the explosion limit. Note that the lower explosive limit level of a flammable mixture and the wider the explosive limit range, the greater the risk of explosion. Mixtures with concentrations above the upper explosive limit, UL, must never be considered safe, as they become hazardous as soon as additional air is introduced. The following 6 factors primarily influence the explosive limits of flammable gases and vapors. First, temperature. Generally, the higher the initial temperature of an explosive mixture, the wider the explosive limit range. Therefore, an increase in temperature increases the risk of explosion. Second, pressure. Generally, the higher the pressure, the wider the explosive limit range, particularly with a significant increase in the upper explosive limit. Therefore, operating at reduced pressure helps reduce the risk of explosion. Third, inert media and impurities. Generally, the addition of inert media can narrow the explosive limit's range. When their concentration reaches a certain level, the mixture may become non-explosive. For example, nitrogen is commonly used for inerting in chemical production. Fourth, container. The smaller the diameter, the more difficult it is for a flame to propagate within it, and the narrower the explosive limits range of the mixture. When the container diameter or flame path is reduced to a certain value, the flame cannot propagate, thereby eliminating the explosion hazard. This diameter is referred to as the critical diameter or the maximum flame arresting gap. Fifth, oxygen content. An increase in the oxygen content of the mixture widens the explosive limits, particularly raising the upper explosive limit significantly. Sixth, ignition sources. The energy of the ignition source, the surface area of the hot surface, and the duration of contact between the ignition source and the mixture all influence the explosive limits. All explosive mixtures have a minimum ignition energy. The lower the ignition energy of an explosive mixture, the greater its risk of ignition and explosion. Next, we will examine the hazards of dust-air mixtures. First, let us define what a dust explosion is. A dust explosion results from the interaction between dust particle surfaces and oxygen. When the surface of the dust reaches a certain temperature, thermal decomposition or pyrolysis causes the release of flammable gases from the dust surface. These gases form an explosive mixture with air, leading to a dust explosion. Therefore, the essence of a dust explosion is a gas explosion. Examples include coal dust explosions in coal mines and dust explosions from the grinding and polishing of aluminum alloy wheels. Factors influencing dust explosions include, first, physical and chemical properties. Dust with a higher heat of combustion is more prone to explosion. Dust that is more susceptible to building up static electricity is more prone to explosion. And dust with a higher volatile content is more prone to explosion. Second, particle size. The smaller the dust particles, the greater their specific surface area, the higher their chemical reactivity, the lower their ignition temperature, the lower explosive limit level, and the greater the explosion hazard. Third, dust suspension. The longer dust remains suspended in the air, the greater the explosion hazard. Fourth, dust concentration in the air. An explosion can only occur when the dust concentration in the air reaches a certain threshold. In this lesson, we have learned the basics of explosions, understood their definition, and analyzed the classification of chemically explosive substances. That concludes this lesson. After class, please consider the following question. What are deflagration, explosion, and detonation? What are the differences between them? Alright, that concludes this session. See you next time.